Okay, this is AP Podcast 6.4, and we're going to talk about activation energy. We're going to talk about what it is and then how you can calculate it. So the first thing, chemical reactions occur faster when the temperature is increased. And this is what we know already. We tested this at the very beginning of this unit. We tested how does temperature affect the chemical reaction rate, and you guys found that it does go faster as temperature goes up. One model that's used to account for the observed characteristics of chemical reactions is called the collision model. And the collision model just says that molecules have to collide in order to react. Here's a picture that we can see. And if we look at this, the nitrogens are all the reds here. These are all your O's. And the nitrogen is the blue. So if we're looking at the top here, if we have the oxygen hitting the middle oxygen off the ozone, and this is ozone, we don't get an effective collision. Both of these, nothing will happen. And also if the nitrogen connects with the middle oxygen on that, we also have an ineffective collision. Nothing's going to happen. What we will see though is if the nitrogen connects with one of the terminal oxygens, one of these end oxygens, that's when we have an effective collision. That's when we get these reactions to happen. So the collision model, you have to have enough energy when they collide, and they have to be oriented in the correct way in order for those reactions to occur. An activation energy must be overcome to produce a chemical reaction. There is a certain amount of energy that these molecules or atoms or whatever they are have to collide with in order for the reaction to occur. And what we know is that the kinetic energy of the moving particles is changed into potential energy as the molecules collide, and that's what's allowing the bonds to break and rearrange into the products that we see. If the kinetic energy is not enough, if there's not enough potential energy being converted, then the bonds can't break and they can't rearrange and we won't get the products. It's an ineffective collision. Only collisions with energy that's greater than or equal to the activation energy are able to react. So I'm just going to do symbols, greater than or equal to. Greater than or equal to, I guess that's greater than and equal to. Here we'll write it in. Greater than or equal to, and then just get rid of that. The activation energy are able to react. So if it's less than that, it's not going to happen. The higher the activation energy, the slower the reaction at a given temperature. So the higher the activation energy, the more energy it takes, the slower the reaction is going to go because the less collisions will have enough energy in order to overcome that activation energy and for the reaction to take place. And this is a diagram we've looked at before. You can see the two different pathways, but what we're really focusing on is the activation energy. So for the forward reaction, your reactants are here, and we're forming our products, which are Y. We can see that this hill, the difference between the energy that the reactants have and the top of this hill, that is your activation energy. So going from X to Y, this is the amount of energy you have to overcome in order for it to happen. The reverse reaction, the activation energy would be a little less because we're starting at a higher energy value. The height of the hill doesn't change, but the difference there does. So the reverse reaction's activation energy would be less for this one. The forward is higher, and we can see when we add a catalyst, a lot of times what it does is it lowers that hill and makes the activation energy smaller, which we know will speed up the reaction. The molecular orientations, and that's what we were looking at in that picture earlier, two requirements must be satisfied for the reactants to collide successfully. The collision must involve enough energy to overcome the activation energy. So when they collide, there has to be enough energy, and also when they collide, they have to be oriented correctly. So they have to hit in the correct way that the reactants are allowed to break their bonds and form any new bonds if they need it. So they have to have enough energy and they have to be oriented correctly in relationship to each other. The fraction of effective collisions increases exponentially with temperature. So as your temperature goes up, your number of effective collisions exponentially increases. It goes up as well. All right, we're going to talk about the Arrhenius equation. And the Arrhenius equation is what allows us to calculate that activation energy. So it's used to determine the activation energy, and that's what this abbreviation is right here. It's for activation energy. E sub A, activation energy. And the frequency factor, which they're going to call A. We don't deal a lot with the frequency factor, but you just need to know that it refers to the number of effective collisions. Okay, here is the Arrhenius equation. Really important that you know that. K is the rate constant. A is that frequency factor that we talked about. Whoa, constant. EA is the activation energy. R is the gas constant, and this is the one we're going to use because we need joules. And T is the temperature in Kelvin. So usually it's going to be given in degrees Celsius, so you're going to have to do a little conversion. What they like to do with the Arrhenius equation, though, is they take the natural log of both sides of that Arrhenius equation that we just showed you, and you end up with something that looks like this. Negative EA over R. 1 over the temperature plus natural log of A. And just like we were doing with the integrated rate laws, this one is also in y equals mx plus b form. And what that tells us is if I plot the natural log of K versus 1 over the temperature, and the temperature needs to be in Kelvin, that'll give me a straight line. And if I find the slope of that line, that's equal to negative EA over R. So this is a very common way that we find that activation energy. You don't see them use this format very often because we don't really deal with A all that much. We use the one I just wrote the most because we like to plot it, find the slope, and then we know that the slope is negative EA over R. So if we know the slope, we plug in our gas constant and we can find the activation energy. So we have an example problem using that, and we get to use Excel again. Yay! So here's our question. The reaction right here was studied at several different temperatures, and the following values of K were obtained. So I have K, the rate constant, at these different temperatures. It wants us to calculate the value of EA, the activation energy for this reaction. So here is our information. All we did was we drug over the data table that they gave us. The format here looks a little different than what we had originally in our problem, but it's just the scientific notation form and how it looks in Excel. So what we're going to do is I'm going to do a few conversions first before I make my graph, because they said I need to plot the natural log of K versus 1 over the temperature in Kelvin. So I'm going to have to convert my rate constant here. I'm going to have to do the natural log of it. So I'm going to do that first. That's going to be equal to natural log of that value. And there's my answer for that one, and I'm going to drag that all the way down to copy and paste the formulas. And then my temperature needs to be in Kelvin first. So that's equal to 273 plus my temperature. And again, copy and paste that formula all the way down so it converts all my temperatures. And then I need to plot 1 over the temperature in Kelvin. So for here, I'm going to take equals 1 divided by my Kelvin temperature. And there's my value right there. So what I'm going to start with is I need natural log to go up the side. So I'm going to set that. I'm going to go to Insert, Charts, Scatter. And there's that. And then I'm going to format the x-axis. Oops, wrong button. I want to select the data that I want for my x values, which I want to be this guy right here. And we'll go ahead and just put natural log of K versus 1 over the temperature. So here's my graph. It should give you a straight line. If you don't get a straight line, you know something probably went wrong. I'm going to see if I can make this a little bigger. Get rid of that guy because I don't need it. All right, so here we go. There's the graph that I have, and that's what I needed. The next thing I need to do is figure out the slope, because they told me that slope is equal to negative EA over R. And so if I can figure out the slope, I can plug it in and solve for the activation energy. Let's see, right click, we want to add our trend line, and I want to be able to display the equation on the chart. So here's my equation. It's really hard to see, but I like it because there's my slope. So in this one, we know the slope is equal to negative 1, 2, and I'm just going to make the rest, well, we'll just use it. We'll look at significant figures in just a second. So that is the slope that's given off of the line that I got. And the units on that are going to be Kelvin. So there's my slope. I am actually going to round that when I plug it into my formula though. So here we go. I'm going to try and write on this so you guys can see. So slope was negative 1, 2, 0, 0, 0. I'm just rounding off some numbers because I don't need all those digits when I'm doing this calculation. Negative EA over 8.3145. So if I solve for this, EA is going to be equal to 1.0 times 10 to the 5th, and that's joules per mole. So I found the activation energy by plotting the natural log of K versus 1 over the temperature in Kelvin. You get the trend line, you find the slope of that line, which we did right there. You plug that into slope equals negative EA over R, and you solve for the activation energy. So there's the activation energy for this question. Okay, so that was our practice problem number 1. The second thing we're going to do is we're going to see if we can calculate activation energy from the values of K at 2 different temperatures using the following formula. And you guys already have this one on the paper, but I'm going to rewrite it so we can talk about it. So we have the natural log of the second rate constant over the first rate constant is equal to the activation energy divided by the gas constant, and then 1 over the temperature in Kelvin for the first rate constant minus 1 over the temperature of the second rate constant. So this calculation, if we just have 2 different temperatures with their corresponding rate constants, we're also able to calculate the activation energy. So our question is here. There's our reaction. At 550 degrees Celsius, the rate constant for the reaction is this. So these two numbers are going to go together, and the 625 is going to go with the 6.4. Those are the temperatures that correspond with the rate constants. It says using these values, calculate EA for this reaction. So here we go. I just did it but smaller so that I could still see the numbers. What I like to do is set up a quick little table so that I can keep track of what goes where. So I have the natural log, or I have K, the rate constant, and then I have my temperature in degrees Celsius. But I need to make sure that when I plug it in, I have temperature in Kelvin. So my first rate constant was 1.1 liters per mole second, and the temperature that went with was 550 degrees Celsius. And I'm going to go ahead just to make sure, I'm going to write K1 equals that, which means I also need to convert this, add 273, and that will be my T1. So those are the two values you're going to use. The second rate constant that they gave us was 6.4, and that was at 625 degrees Celsius. If I add 273 to that, I get 898, and that's my second temp. So ignore those when we plug into this reaction. We have the natural log, and we want to do K2 over K1. So I'm going to put 6.4 over 1.1 is equal to the EA. That's what I'm solving for. It's what I don't know. The rate constant, 8.1345. And then I have 1 over T1, which is the 823, minus 1 over 898. And if I do all that math and I rearrange, what I end up with for an activation energy is 1.4 times 10 to the 5th joules per mole. So 2 different ways that you can solve for activation energy. You can either plot the line, get the slope, and go slope equals negative EA over R, Or you can do it this way using the formula if you have two different Ks at two different temperatures. So that's how you can find activation energy, more graphing, yay, or math, whichever you prefer. Actually, it depends on what they give you. Another good thing to note is your units on activation energy are usually joules per mole, so you can know how to label that correctly. But that's it for this podcast. Arrhenius equation, it's important, we're going to use it, and then let's see, we'll probably be using Excel again so that we can make more graphs to find the slope.